So I'm gonna start. So yeah, thanks for the invitation, and yeah, it's really nice to be here in Moscow. And today I'm gonna talk about Lepski's method. We heard something about it before. Model selection, we've heard something about it before in another setting yesterday. And I'm going to talk about combining. So it was really nice that Andreas was before me because he nicely presented the general approach and lots of the technical conditions. So I don't have to really do this anymore, and you have a vague idea at least how they look like. And yeah, I'm going to treat a special case of penalized likelihood. So first I'm going to introduce the notation and the setup, and then I'm going to see how this finite sample approach combined with this method can be used for model selection. Okay, so the setting, I don't use the term M estimation, but in fact you can think about it in the way Andreas told you. I'm going to consider statistical model P theta. The capital theta is our parameter space, and a quasi-log likelihood L theta. I'm going to omit the y, the observations, which is just, as you've seen before, the logarithm of the Radhanukkah derivative with respect to some base measure. Or you could just start with this object and see what you get. Yeah, we don't assume that the model is a well-specified statistical model, so the true distribution P need not be part of the model. And then we define theta tilde, the MLE, in the standard way. We define the oracle estimate. We saw this before too. It's just the maximizer of the expected log likelihood, which is in fact just the minimizer of the Calvert-Gleicher divergence between the set of the statistical model and the true distribution P. So in the case of well-specified, this is Ah, yeah, okay. Okay, then, yeah, we, as told you before, we study non-asymptotic results in a finite sample case where we have a fixed size n, so we try to control all the little terms which appear normally in asymptotic results and are thrown away. And with our misspecification, and one example is adding a penalty to the model. So the building blocks are just some localization scheme, the local quadratic approximation of the expected likelihood. Andreas showed you the condition with the delta, and a control of the stochastic part of the likelihood by exponential conditions. So in our setup, we assume that the parameter dimension of the space theta is larger or of the same order as the number of observations n, or perhaps even infinite, but I'm going to stick to the situation where we have about equality here. And well, in the case where we have this larger than n, then we have problems with identifiability, we have problems with overfitting. And so the natural way to deal with it, as shown by Peter, Bayesian setup, or like many people do, is just add a penalty term here, a quadratic penalty term. So this will be our G will be a penalty matrix. So our penalty operator, if we are working in infinite dimension, lambda will be a tuning parameter for the strength of the penalty, which will be in some set big lambda, which could be the whole positive half line or a smaller set, or even a finite set in your case. So I'm not going to explicitly say. And yeah, so to define the Hessian, delta lambda square is just the minus the Hessian of the expected value of the likelihood here. So everywhere we put lambda for the likelihood with the tuning parameter lambda, penalized likelihood, and this is the oracle of lambda. This is just the brains of the score. As I said, it's the Fisher information. And what we have inequality between these two, which is in the well-specified setting, is the case. And this lets us define again in concordance. It's not exactly the same, but in our setup, we also have our effective dimension, which is really close to Peter's. It's a trace of b0 squared times b minus 2 lambda, which would be just the dimension of this parameter space P if these two would be the same, of course. And psi lambda is the normalized score, normalized by the square root of the Fisher. So one example is a spline regression. Observe a function which we don't know at some design points, add some noise, and this problem is not identifiable in this setup, even if we assume some smoothness assumptions. So we add a penalty on the average curvature, for example, with a second derivative to get identifiability, and then one can even show that we reduce the problem to an n-dimensional subspace. And I'm going to consider cases now where we assume that the parameter space theta is n-dimensional, and I'm going to simplify our setting a bit more in comparison to Andreas' general setup. I'm going to consider that the stochastic component of the likelihood is linear, and we assume some exponential moment condition on this score normalized by its variance. So in every direction, in fact, it is sub-Gaussian.
The n is the same, n is the sample size?
Yeah. Okay. So, as I told you before, I'm going to consider, like, if you think of spline regression, then normally you can, by imposing set, or in general reproducing kind of Hilbert space setups, you can often, like, get to a parameter dimension which is close to the sample size, or the sample size, just by adding the penalty and excluding certain types of possibilities of MLEs. So, yeah, so I'm going to include the n-dimensional setup, but you could change it a bit too. Okay, and then you have this sub-Gaussianity condition plus some other technical conditions which Andreas alluded to. So first, under these assumptions, we get Fisher's expansion. Everything is a bit simpler. We have this psi lambda here, which approximates this rescaled MLE and centered and rescaled MLE. This diamond term would be the tau of Andreas' talk. So I'm sorry we didn't really talk about our notation beforehand. So, but think about the tau. So I make it depend on the x, the r, and the tau, which Andreas showed you is already chosen in this setup. So I have this. So what I have, I say that with very high probability, depending on x, I can approximate nicely this guy by psi, and with this error, which will be small and will get smaller and smaller as n grows. That's the hope. And for this object, we have sort of chi-square variable bounds, as you see in this, as we are treating sub-Gaussian case. That what you get, and exactly we define this z lambda x, which will appear quite often in the following. So we define this guy as p lambda plus this middle term plus this 2x. So we have here the effective dimension appearing, and here something like the variance of this quadratic form, which is this object. And yeah, to give you an idea of this, we already saw that this diamond term, if you have a nice IID setting, then it scales like this with the effective dimension n. So now we have to do model selection, so bias will come into play. We define this, the b lambda, as the bias of our, the difference between the theoretical estimate for a fixed lambda and our true parameter, which will be in fact, which will be in the, for example, this spline example, which would be this theta star would be the oracle parameter without penalization. But on the n-dimensional space, so this would be a spline which passes through all the true function values in the design points. So not necessarily the real function behind it, but something very close to it, which approximates really nicely. So, but if you just consider the problem abstractly, you can call it the true parameter. So this is what I'm going to do. And this is just the difference in the oracle parameters, which I'm going to write like this. So now we have a notation in hand. To use Lepski's method, we will see that we will need confidence bands for the values of our estimators for different penalization parameters. So I'm going to try to introduce these results beforehand and then show Lepski's method to you. So the setting here is we want to assume general forms of losses. We assume a matrix W square, which is in a semi-order, logical semi-order in matrices, common is smaller than all the d square lambdas in our set of penalization values. And what we are interested in now is to control, on one hand, this W-weighted loss true parameter against NLE, and the differences between two different NLEs for different penalization parameters. These guys we are interested in. And so just one can uniformize, in fact, the results I showed you before, to have for all lambda in our set under some technical conditions we can uniformize the results we saw before by saying that we can bound this by this psi lambda W, which I will define like this. So that's another quadratic form, square root of a quadratic form, this guy here, plus some the diamond term you saw before, and this bias term B lambda. And we have a similar result for the differences. If you have lambda smaller than lambda prime. Yes.
Where does this n come from in probability? I mean, does it is the size of lambda big lambda or what?
This n comes from so basically you first split your parameter. So you have your, so let's say this is your all lambda or from 0 to infinity, and then you split it according to the p lambda values. So you take p lambda equals 1, p lambda prime equals 2, and so you split it in n different subintervals, and then you just do like a brutal sum estimation, and so you obtain this log term, you put it in here by this. And here you have comparisons, so you get the n squared. So, and I have these objects in top. Okay, this one out. Okay, and then you want to control these objects here, and you can find uniform bounds for deviations of these objects too, which can be nicely bounded in a similar form to the one we saw before, but with a payment in log n, about log n times some constant. And here are the expressions for the bounds. They look really similar to the ones we saw before in the 1 lambda case. Just our effective dimension got a bit more complicated, and here it got even more complicated. And these two guys I didn't write down because they're just the squares of, you can imagine, and they're not that central. So now we have confidence bands for in a uniform way to compare different, so to compare these guys in between each other, to these guys uniformly bounded. Now we want to use this to do model selection and use Lepski's method. So I'm going to give the main idea of Lepski's method and then show what we got there, like results. So the aim is to find a good estimator of the Oracle penalization parameter. What means good estimator of what means Oracle penalization parameter? You give yourself some loss, for example, this quadratic risk with respect to this W matrix, or just the norm, the expected norm here, and you look what would be the minimizer lambda, and you could call this guy lambda star, and then to find this, you want to get an idea how the bias at this best minimizer behaves, and you want to see want to test the hypothesis first simultaneously for all lambda prime smaller than lambda that you have equality between the NLEs, so nothing big changes, and if this equality can be rejected on the assumption that bias is of the same order about as the variance. I'm going to explain this a bit more in the next slides. And W here could be D0, for example, so the non-penalized Hessian, or it could be some projection on some smaller subspace, still under this condition.
So identity will not work, or will work?
Depends on the D0. So I mean, in a nice case, if you can think of a Gaussian case where your D0 is just identity, like some sequence space model, then it would work. But need not be. So you need that. In fact, yeah, you need to. At some point, you would like to replace the W D minus 1 here by something which is smaller than 1, and you can put it out. So what we need is the control on the stochastic part of our risk and an idea how the bias behaves in comparison to the variance, especially around the oracle parameter. So we're just going to use like definition of our bias, no matter what kind of risk we are considering, and we consider that this is sort of the stochastic variation as we saw on the uniform bounds of our of the difference between two estimators, and so we're going to so assume that this times alpha, this is stochastic variation times alpha, is bigger than the maximum of the bias, standard bias, or the difference in bias between lambda prime and lambda for all lambda prime smaller than lambda, smaller than our oracle parameter.
You view it as a bias variance trade-off.
Yeah. Sure.
So basically, so lambda prime smaller than lambda star means that you're penalized less, and therefore bias is smaller intuitively. The less you penalize, the smaller is the bias. Yeah?
Yeah, of course.
And what you say, below lambda stars there is no significant bias compared with the corresponding standard deviation of the stochastic part.
Yeah. So and we put this in as an assumption, but it's fulfilled if you look at Piaget's paper, or like, if you look at Lepski's method in this. In some saying, this is normally fulfilled. Sometimes one of the nice cases. So and then yeah, the next trick lesson is so we want to choose our estimator now. We say we look at the differences of the MLEs in lambda prime and lambda by W, scaled by W, for all lambda prime smaller than some lambda, and we say that lambda is accepted for all lambda prime and smaller than lambda. We have that this guy, this would be like the stochastic variation which we saw in our confidence bands, sort of. This guy plus what we could expect in maximum as a bias if we are below the oracle. They are bigger than this object, which if we use the triangle inequality can be split in some stochastic part and some bias part. And then we define the so the biggest lambda tilde where all lambdas below are accepted as our estimate. And now we want to compare this object, the estimator we get, the MLE we get with this object in comparison to the oracle estimate. So the idea then is to split in two zones, first oracle accepted or oracle not accepted. So our estimate is bigger than the lambda star or smaller than lambda star. And the first zone means we tend to oversmooth, we select fewer dimensions than we need, or fewer degrees of freedom. And the second would be that we select more dimensions than we need. And so how do we go about to generally show results? This is a simplified setup. In this direction it's easy, we just split by triangle inequality this guy into the bias and the stochastic variation. We split this guy by triangle inequality into this oracle loss here, and here we would have a difference between this MLE and this MLE, and by definition of our estimate we know that this we can bound this by such an object about, and that's what we do here. We split here and then we bound and then use some supremas in some places. And the second region means that we didn't go further than the oracle estimator. This should be very improbable in the way we constructed it, looking at the confidence bands we showed before, because we will have this guy is bigger than this and this, this guy we can split again into the bias and the stochastic part. We know the stochastic part is with very high probability smaller than these two guys together, and the bias is smaller than this guy because we assume that we're in a setting where we are below the oracle by assumption. And so this should work too. And then in a probabilistic setup, this will give us this following result. We put everything together. We can bound the deviation probabilities of our estimator by the stochastic variation terms, which are in terms of this oracle estimate, plus something which will drop to 0 if n gets big. And here we have a constant which enlarges our terms. And we pay by some log n factors that we put them up here. So, and this is, I mean, Lepski's method is normally with moments, so we can do the same with moments, and complications get more complicated. You have to control more terms and get bigger rest terms here, but we get a similar result, for example, for the L2 norm here, the expected L2 norm. We get, here we have the oracle risk plus some term which is 1 plus alpha times something which, if we haven't fixed the x, seems to be in the order of the oracle risk, plus some terms which will, under nice choice of x, go to 0. And so the question is, what is the nice choice for x? If you look at this, it's just a repetition of the last slide, what we have that there. So we should choose, so we can see that we should choose x with some k times log n, and that that will give us that this guy goes to 0 at least as fast as this guy, so we can choose a k such that this is the case. I mean, this won't grow too fast, we know this. I won't show you the term, it's quite long, but it just grows polynomial in n or in x. So we can just take some log n factor here for the x. And so this will really dominate if we take k high enough. And this will go to 0 too. And so we have, so these two terms are more interesting. So here we have just the oracle risk. Here, if we put in here something with log n, then if our lambda star grows with n in a way that the effective dimension p lambda star grows faster than log n, or considerably faster than log n order, then this will just be of about of the order of 1 plus alpha, this guy, one could suppose. So this is the case of sort of the global estimation setup. And if we don't have the case that this p lambda star grows or fast enough with n or grows at all with n, more of like some point estimate setup, then this the log n term which you put in here, look at this form, I mean that's the general form of all the things we saw. So there you have a p lambda, there you have an x. Here we have a log n, and here we have something which does not grow, so this log n term will dominate. Or in fact, this 1/2 is square root, I forgot to mention it, so this square root log n term will dominate here. Will dominate here. And yeah, and this resembles more the Lepski results on point-wise estimation, where you can get the optimal risk if you have to pay a log n term. So it's not 100%, it's work in progress. I would say it's 100% the same, but I think the same ideas appear here. Yeah, and that's what's written here about it. So what's the difference between what I did an existing result? It's normally in this kind of model section that people consider Gaussian models, often linear estimators or even projection estimators, which makes the whole analysis a bit simpler. And so we use sub-Gaussian error structure, and we didn't assume linearity of the estimators. The MLE could be a linear estimator. Which in this combination I didn't see that it was treated so far. So if there are any examples.
Exactly. I think if you want to apply, say, the Gaussian context, then you do not need any assumption on the type of estimators. You have just
I mean
the selection of estimators. However you got them.
I mean the combination of
The
the
combination.
two.
You are right. But in general, it's not important. How do you obtain the estimator? You just have estimators.
Yeah, okay, but yeah, perhaps I saw a couple of papers on Gaussian with linear estimators, but perhaps there are even more general papers where you. Yeah, exactly. So these are the two main differences, and we hope to really have a uniform framework for the global estimates and the local estimates by choice of W, for example, which could be projection or not, and then see the behavior and the transition between the behaviors. So this would be interesting if we get this. Okay, so thank you for your attention.
Questions?
You said your parameter space has dimension n, same as the sample size.
Yeah, but
then your effective dimensionality must somehow be smaller, or how is that?
That's the idea.
So what is p lambda then for some relevant examples? So of what order of magnitude?
So I mean, if you have so p lambda in theory, if you looked at this object which we considered, it could be as high as n if you consider lambda equal to 0. So, but then in the application of the theory, you have these diamond terms which would be very large for you who are n the effective dimension bigger than n1/2.
And small p lambda corresponds to strong penalization, I suppose, or?
Exactly. So this is just think about a projection estimator, for example, then just think about the dimension of your projection you take. And so the model naturally selects lambda which is small enough so that the diamond terms don't explode, because then if you look at the way it's defined, it shouldn't work. And you would like some bounds on the p lambda star from below that it's not, so from above, the p lambda star from above, so that it doesn't grow too fast with the dimension to really have, you can apply your method. Otherwise you should cut at some point and see what it gets. So I can't tell you, that would really depend, I think, on your application, because what we are considering here is p lambda w, which then, if w is some kind of projection, then you're in a sort of semi-parametric setup, so it would be a lot smaller. If you consider the d0, so you try to get the whole dimension, so there's no typical value.
But actually, because lambda is chosen by Lepski's method, you don't know the effective dimension at the end.
Yeah.
No.
Well, you cannot predict, so to speak. You can calculate.
For each particular lambda, you know the effect.
Yeah, you can calculate that.
But for Oracle model, you don't know.
Something is a nice function of lambda that governs the impact of lambda.
No. So in fact, again, back to the Lepski method. So in fact, I'm also contributed a bit to this method, but there is a general critique to this method that it's not a method at all, first of all, because the method is supposed to select one parameter, lambda. And there are another tuning parameters involved, which actually there are more tuning parameters involved than lambda. Just one lambda, and if you don't specify how to select those tuning parameters, then you translate one problem into another. So this is one critique, and the other critique is that in fact there is a gap between theory and practice. So this gap is in your notation is hidden in your z function. So you don't calibrate your if you show your procedure. You show the procedure, not the result, but the procedure. Okay. So here, in fact, you have some conditions on the z which involve something like log n, and if you takes it from this expression, it appears to be much too conservative. So it doesn't work at all. So it's like Bonferroni correction in multiple testing. So in fact, what we are doing is multiple testing, and the proposal we showed is a Bonferroni correction, multiple testing. And this doesn't work. In multiple testing doesn't work, in model selection it doesn't work as well. And the idea is, in fact, to make another calibration, which is more sophisticated. And the point is you have different tests, but test statistics are all dependent. If you take another pair of lambda prime lambda, it's still based on the same data, original data. So your test statistics, which you compare with the threshold, are all dependent. In fact, a careful choice of upper function, what is written on the right, is called upper function. So basically, you take the differences and you say, I take the largest lambda, so that to the left of this lambda, I don't see any bias. Everything is below this curve, this upper function. So this is the choice, and you are interested to make this upper function as small as possible. And if you do this Bonferroni correction, it will be much too high. It doesn't work, and this is a general critique. The Lepski procedure, the usual justification requires this local correction. In practice, it doesn't work. And the big challenge in the whole story is...
You really would have to use the covariance structure here.
No, you don't use covariance
structure.
Dependence, I mean dependence structure.
Even covariance is not enough, but dependence is correct. So I mean, the whole structure of the whole process need to tilt lambda. But so I mean, it's not so dramatic. Don't worry. So everything is already on the way. So we just outlook where we work to modify this criteria to improve this function, upper function ZW. So this is a great challenge. So to the left, you indeed have all the time this very simple check. So basically, you compare different estimators and check whether there is significant difference. If there is significant difference, it's only because of the bias, and this means you made over smoothing. And you increase lambda until you see this significant difference. This is the whole idea.
Yeah, but then one can also take a further thing into account. You do not test all these hypotheses like individually, but they are pre-ordered. You start with a certain hypothesis, and only if that one is rejected or not rejected, you move on to the next one. So
this is exactly the procedure.
Yeah, but then you could even choose the upper function better by taking this selection mechanism into account additionally.
But then you cannot prove the theory. Unfortunately, then probably you can control FDR, but you don't control the family-wise.
But life is much easier, because in practice, you penalize the square of log n, but the prefactor, which should be 4 in theory, is always 0.1, and that works nicely.
But the theory doesn't work with this prefactor.
No, the theory does not work.
No, and that's all about. So we want the theory which works, and not the theory, not the gap between theory and practice. I know what you say about this, but actually there is a theory which justifies the procedure. So you can select this upper function. Theoretically, it will work. So this is not a big deal. This is called propagation principle, and we will try to work it out.
So work in progress.
Yeah. Okay. Any
Propagation.
propagation of the work in progress. So, any further remark?
For example, if we add additional divisor with lambda 2 and lambda 1 with the previous, how would we use Lepski method to accept the largest? So how we compare?
You would have to need an order there.
So unordered case when lambda is not ordered, not univariate.
Yes, in space errors.
Now, there's another direction of outlook, another direction of extension. So this is actually the topic we are working on. How to do Lepski type model selection for unordered or partially ordered set of lambdas. When lambda is a vector. A particular case which Kirill is working on is when lambda is set of all subsets. So you have a lot of features and you select subset of features, and then of course this is so your lambda is a subset of the whole set, and then of course it's partially ordered, and you have plenty of possible choices of lambda.
And so the bias structure is supposed to the intent. What is stronger?
But also maybe there could be some optimization tasks, for example, to make a gradient step when we have dimensions.
How to find the solution? This is another issue. I don't know. So sometimes you can solve it effectively. For some examples, I am not sure that there is a general procedure. So, okay, if no further questions, let's thank Niklas.